Video is about linear regression, a statistical method for modeling data. The data set we're going to look at is the population of the United States from 1790 to 2000. The first thing we would need to do is to enter the data into the list in our calculator by going to Stat. I've already entered the years in list 1 and the population in list 2. First population number is in scientific notation 3.93 times 10 to the 6th. Each of these list 1, list 2 numbers represent a point on a graph. And if we want to see that graph, we need to go to second y equals, which is stat plots. We need to turn a stat plot on. And this upper left plot is highlighted. That's the scatter plot. You can also see histogram and box plot here. We need to make sure that the calculator has proper lists in the X and Y list. So I'm going to tell the calculator that the years are in list 1 and the population is in list 2. And we also get to choose which mark we want to make on our scatter plot. I'm going to choose this one on the left. Next, to create a window that will capture this data, we can go to Zoom 9, which is Zoom Stat. And a window will be created for us. And here's the data graph. What we can see is there's a positive relationship between population and year. As years increase in value, so does the population. There's also some curvature that we can see in the data, which means that there might be a different model that fits better than a line, but we will talk about that later in the year. For now, we want the calculator to come up with the best fit line for this set of data. Before we do that, we're going to turn diagnostics on in our calculator that will give us additional information about how well our line fits the data. We want to go to second 0, which is catalog, and then we can go to this key, which is the D key, and then scroll down until we get to diagnostics on. Enter twice. And once that's done, you don't have to do that again. Your calculator is now set with that. Now, to run the regression, we go back to stat calc, which is where one variable stats is also that you used in chapter 1. Now we go to number 4, however, which is linreg, linear regression, and you can see something that looks like part of the slope-intercept equation of a line here. We're going to enter here, and we can tell the calculator which lists our data are in. So list 1 and list 2 are the default lists. So if that's where your data is, you can skip this next step. But it's worth remembering to do this in case your data is in a different list than list 1 or list 2. So I've now told it that. And before we run the regression, I'm going to tell the calculator to put the line equation, which is our model, into our y equals list. So I'm going to go to vars, which stands for variables, go to y variables, function, and then I get to choose which part of the y equals I want to use. I'm going to use y1, so I hit enter. Now the calculator is going to do a lot of calculating that will take us a long time, but it's going to do it in a matter of seconds. And it comes up with this information. First, you see the slope-intercept equation of a line. The slope here is a little over 1 million. And the y-intercept is this negative large number. We'll learn how to interpret these more in class. I do want to mention little r. This is what we did when we turned diagnostics on. The closer r is to 1, the more perfectly our line will fit the data, and also tells us that the data has a clear linear relationship. Also, if it's positive, as it is, then there's a positive correlation. So as years increase, so do population number. If it was negative and close to -1, it would be a nearly perfect negative correlation. The closer this number is to 0, the less of a pattern there is to the data, and the less correlation there is between the two variables. A correlation coefficient of 0.959 is actually quite high, so this should be a good fit. If we look at the y equals, we can see that the calculator did put the equation into the y equals list for us. And now if we just hit do 9 again or graph, since the window is already set, we should be able to see how well our line fits. Okay, so what we see is the line is underestimating at the beginning, so our model underestimates population, even to the point where it says it's negative in the 1700s. It's overestimating through the 1800s and most of the 1900s, and then it underestimates population again after 1960 or so. What we can do once we have a model is pretty powerful. We're able to predict or make estimations of the population for years other than noted in our data set. For example, here's a list of questions. We could ask, according to our model, what would the population have been in 1965? Well, 1965 is clearly inside our set of data between 1960 and 1970. If the prediction is inside the data set, we call it an interpolation. In order to do this by hand, we would simply put 1965 into our model for X, since 1965 is a year, and we would just stick 1965 right in here. The calculator can do this quickly for us. If we go back to the home screen and we go back to vars, yvars, function, y1, and we're going to just tell the calculator by putting parentheses and then the year, 1965 here, it will plug 1965 into our model and tell us that the population would have been about 185 million people in 1965. If we look at our data set, that does fall in between the values for 1960 and 1970, so it seems like a reasonable estimate. The second question asks, according to the model, if the population trend continues, what should the population be now in 2011? Well, if we go to second enter, we can just edit the year and change it to 2011. So we could make many predictions relatively quickly now that we have our model. Hit enter. And the model tells us that if the trend continued and if our model was accurate, we believe that there'd be about 244 million people in the United States today. Looking at the data, we can see that that is a poor prediction in this case. And remember that our model was underestimating when we got near the year 2000 and certainly 2011. And so a value of 244 million is considerably lower than what the current population is, which is closer to 300 million. When you make a prediction outside the data set, so before 1790 or after 2000, it is considered an extrapolation, and these are less precise. Final question asks, according to the model, if the trend continues, when will the population of the United States reach 500 million? So here we're told a population number, which is a y, instead of an x. So if we were doing this by hand, we would have to enter 500 million for y1 here and solve this equation for x. Using our calculator, we can enter 500 million in our y list, which I've entered down here at y7. And for the graph now, our window won't be able to reach 500 million. But if we zoom out, zoom 3, and enter, we can see our model, and the data is all scrunched up, and we can see the line y equals 500 million coming across. What we want to figure out is what is the x-coordinate of this intersection point, because that's going to be the year that corresponds to the population reaching 500 million on our model line. So we need to go to second trace, which is calc. And when we do second trace, we have this option of intersect, number 5. As for first curve, we can just hit enter. Second curve, enter. Yes, enter. And it determines that the population, according to our model, will reach 500 million in the year 2209.